All right, on this problem, we want to look for the exact length of the curve. So that's a little bit different than the first one that we were working on. With the first one, we were able to use our calculators and kind of do some cool stuff, but we're going to follow the same process. We've got a y equals equation, and since our equation says y equals, we get to use the y equals version of the length of the curve, and so I'll just write it out right here for us. The length of the curve is equal to the integral from a to b. In this case, it's going to be 0 to 1 of the square root of, and then it's going to be 1 plus y prime squared. Or you could also have dy dx in there. Okay, so remember, y prime is equal to f prime of x, which is equal to dy dx. So all of those can go into the parentheses there. This particular guy looks a little bit on the gross side. So what we're going to do is we're going to find derivative, which is, if you break it down, it's 4 square roots of 2 over 3 times the derivative of this part right here. So that's going to be 3 halves times x to the negative 1 half, sorry, to the positive 1 half. And then the derivative of 1 is 0. So clean this up a little bit, and you end up with the square root of 2 x to the 1 half power. Okay, that certainly doesn't look too painful. And so when we substitute it into our formula for the length of the curve, the exact length, then we're going to go from 0 to 1 of the square root, 1 plus, and then our derivative squared, so square root of 2 x to the 1 half squared dx. Here's the cool thing on this problem. When you square out this guy right here, the square root of 2 squared is 2. That's nice. And the square root of, whoops, there should be a 2 right here. So that's 2 square roots of 2. And the square root of x to the 1 half squared is just x. So we're actually going to work with a much simpler integral. The square root of 1 plus, and then 2 squared is 4, times the square root of 2 squared is 2. So 1 plus 8x dx. And the dx is not under the radical, so let me make that clear. Okay, so once we get this done, we can integrate that because now we're dealing with a situation where we've got 1 plus 8x to the 1 half power. And so when you integrate that, remember the derivative of 8x, okay, chain rule here. So we're going to reverse chain rule. Derivative of 8x is 8. So I want to put a 1/8 in front of this guy. From 0 to 1. And then this is just integrating now the square root of all of that. 1/8. So if I integrate a square root, I add 1 and divide by the new exponent. So this is going to be 1 plus 8x to the 3 halves divided by 3 halves. Okay? And how do I know that that's what it is? Because when I integrate 1 plus 8x, that's inside the square root. And so when I integrate a square root, I add 1 to the exponent. So 1 half plus 1 is 3 halves. And the 8 I account for with the 1/8 part. So then I divide by a fraction, which means I multiply by its reciprocal, which is 2/3. So I have 1/12 times 1 plus 8x to the 3 halves power, evaluated from 0 to 1. Okay, so I'm going to come up here where I got a little bit more space, and we're going to finish this guy off. Now I do my stop minus my start, so I stop at 1, so it's going to be 1/12 times 1 plus 8 times 1 to the 3 halves minus 1/12 times 1 plus 8 times 0, which is going to be 0 to the 3 halves. So it looks horrible, but it's really not too bad. So this is 1/12 times 9 to the 3/2. Okay, that's the square root of 9 cubed. That's 27. Square root of 9 is 3. 3 cubed is 27. So 27 over 12 minus, and then 1. So 1/12. And that's going to give us 26 over 12, or 13 over 6. And that's the exact length of the curve, 13 over 6 units, whatever we're talking about, okay? That's it. It's not too bad. And if you punch it into your calculator to double check, you'll get whatever 13 divided by 6 would be as a decimal.